I thought that I had a video deriving this, I don't. So I'm going to do it. I want to derive the electric field due to two parallel charge plates. Let me switch over to Python real quick and show you. I already made a video on this, but I want to show you what it looks like, a different way to do it. So if we switch over here to the computer, this is a Monte Carlo calculation of 5,000 charge points on two plates. And then I calculate the electric field at a bunch of locations to show you that the electric field's constant inside. It's not obvious that it's constant inside. And then on the outside, it's very small. Well, there it is. The electric fields are very small on the outside of the plate. This is one side. And so I want to derive this with calculus. So let's jump back over to the paper, and I'll tell you why I'm not going to use Gauss's law. I'm having trouble thinking. Okay, there. So the basic idea is to find the electric field due to this positive charge plate and a negative charge plate. And the first thing I'm going to do is find the electric field due to one charge plate. And so if I just want to find this, I'll put the charges on this side. It doesn't really matter. And I want to find the electric field right here. Now, a lot of people are going to say, oh, you could use Gauss's law. You draw a pillbox like this, and then you calculate the flux in the two sides and the total charge inside. And this is fine. Gauss's law is fine if you have to know if you know E is constant. Right? Because you have to know that the electric field is constant in both magnitude and direction. Otherwise, this whole thing won't work. If the electric field changes with distance and you make this thing bigger, then you don't know how that changes because you don't change the amount of charge inside. And you can make the argument, well, if it's an infinitely sized plate, then it couldn't change, and I get that. But I don't like that, so no, not going to do that. Instead, we want to find the electric field due to one plate and then two plates. And the best way to find the electric field due to a plate, if I have, I'm going to use a circle, and I want to find the electric field on this is the z-axis. It has a radius r and a total charge q. Well, what I want to do is to find the electric field due to an individual point, which is 1 over 4 pi epsilon naught q over r squared r hat, where r is the vector from the charge, wherever the charge may be, to where you want to find the location of the electric field. And so I have a bunch of charges here, so I have to find the electric field due to all these charges. Now, in the Monte Carlo calculation, I just did that. I just manually found the electric field. Well, I made Python do it. That's what's great about Python. But now I need to do break this into tiny charge pieces, dq, and then integrate over the surface area of this. You could do, a Cartesian integral, surface area integral, which is not easy because if I call this the x and the y axis, then my limits of integration are tough. I could do a polar coordinate integral, and that wouldn't be too bad. But let's do a different integral. I don't want to do a double integral. So let's take our disk, and I'm going to draw it from the side just to be clear. So looking at it from that, there's my z-axis, like that. And I want to find the electric field at some point right here on the z-axis. That's the first step. And what I'm going to do is to take my disk and to break it into rings. And then I can just, once I find the electric field due to a single ring, I can integrate over r and add up the electric field due to all the rings. So let's say this is a ring. This is a ring of radius r with total charge q. And I want to find the electric field right here. Well, again, I'm going to take this and break it into a little piece. I'm going to call that dq. I use the lowercase q. And this is a distance z on the z-axis. And that, assuming this is a positively charged ring, it doesn't really matter. I'm going to find this distance is the distance from the ring to from the point charge to my observation location. And this will be dE, the electric field contribution due to that one piece. So I do need to find that distance, which I'll do in just a second. But the trick here is that if I look at this piece down here on the opposite side, there's another dq. and it makes an electric field like this, and it has the same distance, has the same charge dq, so it's going to have the same magnitude, but the direction will be different. But these two will cancel in the non-z direction. So every point on here is going to have a component in the non-z direction. Okay, so let's write an expression for the z component of this electric field. So let's call this angle theta, and that's the same as this angle theta right there. So I'm going to write dE z is 1 over 4, it's a point charge, 4 pi epsilon naught dq, I use lowercase q, over, I'm just going to call this r, lowercase r squared. That's the magnitude. Now I need to find the z component. So I'm going to just take cosine of theta, and I don't know what theta is, and that's fine. So that's my z component of that charge, the electric field due to that charge. Okay, let's go ahead. We need to find r, and we need to find cosine theta. So let me redraw this a picture right here. I'll make it a little bit bigger. So if I have that as my angle theta, that is capital R, that's z, that's r. So I know here that r is going to be equal to the square root of r squared plus z squared, right? Because it's a Pythagorean theorem. I also know that cosine theta is going to be equal to the adjacent over hypotenuse, which is going to be z over r, which is the square root of r squared plus z squared. So we can put both of these things in over here. So now I get dE z 1 over 4 pi epsilon naught dq over r squared, which is this squared, r squared plus z squared. And when I say r squared like that, can you hear what I'm saying? R squared, that's capital R. When I say r squared, that's lowercase r. Can't you tell the difference? I'm saying it. Okay. And then cosine theta is this, z over this. I'm going to put this as r squared plus z squared to the 1/2. And that's my dEz, and I can combine these two together to get 3/2. This is just 1/2. Now, when I integrate, what's going to change as I go around the loop? Well, r is constant, z is constant. All I have is dq. So let's write this as the total electric field, Ez, is going to be equal to all this stuff, 1 over 4 pi epsilon naught z over r squared plus z squared to the 3/2 integral. I'm just going to write it as generic integral of dq. And so I'm going to integrate over all q. Well, that's pretty easy. That's just going to be the total charge q. And there we have it. Now we have the electric field on the z axis due to a ring. Ez 1 over 4 pi epsilon naught. I have z and then I have that q, which I'm calling capital Q. Z q over r squared plus z squared, that's a squared, to the 3/2. And that's just the z component. Now, let's check. That's a check. Check. Number 1, units. So remember that the electric field due to a point charge is 1 over 4 pi epsilon naught q over r squared. So this has to have the same unit. So I have the 1 over 4 pi epsilon naught. 4 pi doesn't matter. I have the 1 over epsilon naught. I have q on the top. That's good. And then I have meters over this. So this is meters squared to the 3/2, which is going to be meters cubed, but then I have a meters on the top. So I do get the same units. Check. Let's check as z, if z equals 0. If z equals 0, if I go back over here, and I would be right in the middle of a ring, then if every piece I take would have an electric field on the opposite side that cancels. So all the electric fields should add up and be add up to 0. So I should get 0 electric field at z equals 0. If I put in z equals 0 here, I get 0 on the top. I get r cubed on the bottom. So it is 0. Check. What about as z is much greater than r? Well, if I get really far away from this ring, what should the electric field look like? Well, if I'm really far away, or if the R is very small, it's like a point charge. So if R goes really small, then I get EZ equals 1 over 4 pi epsilon naught Z Q. And then if this R is small compared to Z, I can just write this as Z squared to the 3 halves. And this is 1 over 4 pi epsilon naught Q over Z squared, right? Because I get Z cubed, I get Z. So that's the point charge. So that looks good. Okay, so that's important right there. Looks like it's good. Now let me rewrite that because I'm gonna get messy. I feel I'm being a little bit messy here. EZ, and this is due to a ring, equals 1 over 4 pi epsilon naught Z Q over R squared plus Z squared to the 3 halves. Remember, this is only on the Z-axis. If you go off the Z-axis, this does not work. We could find that, but we're not going to, which is possible. It's just more complicated. Now let's go back to our disk. So here's our disk. I'm going to draw it from the front. And I'm going to break it into rings. And that's a terrible drawing, but that's fine. So this has a total charge Q. So this ring will have a charge dq. And we'll say it has a radius lowercase r, and the radius of the disk is r. So each ring is going to make a contribution to the electric field on the z-axis. So I can say DEZ is going to be, it's just this. Each ring makes this. But the radius of the ring is lowercase r. Okay. So I'm going to say 1 over 4 pi epsilon naught z. It has a charge dq, which we'll need to find, over r squared plus z squared to the 3 halves. And so we're going to add up from r equals 0 to r equals r. And so we're going to integrate over r. We have an r in there, but we need to get rid of the dq. So we need to get dq in terms of dr. So let's imagine that the charge is uniformly distributed. If that's the case, the area of the ring, a ring, divided by a disk, is going to be equal to the charge on the ring, dq, divided by the total charge q. So the area of the ring, this is actually has a radius of r, so it has a circumference of 2 pi r and a thickness of dr. And if you imagine if you broke this out like a long rectangle, this would be 2 pi r, and that's dr. And now you can say, oh, and that's not quite true because it's not actually a rectangle, but dr gets really small, so this is actually okay. And then the area of the whole disk, it's just a circle. So I get 2 pi r dr, that's the area of the ring, divided by the area of the disk. It's going to be pi capital R squared. It's just a circle. And that's going to be equal to dq over q. So I can solve for dq. I get dq equals, the pi's cancel. I get 2q r dr over r squared. Is that right? Q, the pi's cancel, 2. Right. Now I can put this in up here. So I get DEZ equals 1 over 4 pi epsilon naught z. dq is going to be this. I'll just put it as 2q r dr over r squared. That's my dq. And then I still have that, r squared plus z squared to the 3 halves. Now I can integrate, right? Because everything in here is a constant except for the r's, so I can write this out. So let me start a new sheet of paper. You know, sometimes you think, oh, I need to save space, but sometimes you just need to go all out. and just use a lot of paper. So I'm going to say EZ is going to be the integral from r equals 0 to r equals r, 1 over 4, actually the 2's cancel, 1 over 2 pi epsilon naught. I'm going to pull all the constant stuff out front. I have z q, and then I have an r squared, and then I have r dr over r squared plus z squared to the 3/2. Okay. I remember one time someone said a comment, you say okay too much. Okay. You got to just do it your own way. You got to be you. If you say something too much, that's fine. That's just who you are. This stuff is all constant. I'm going to pull that out front. So I have z q 2 pi epsilon naught r squared. And then I have the integral from r equals 0 to r dr r squared plus z squared to the 3/2. Now, you may say it's time to Google this thing, or let's get out the math table book and look up the integral table. But this is not impossible integral, right? If you look at this, you see on the bottom I have an r squared term. And if you take the derivative of r squared, you're going to get something like this. So this says, what if I let u equal r squared plus z squared? Then du is going to be equal to the derivative of this, which is 2r, but then I have to take the derivative of r, which is dr, and then the derivative of z squared is 0. It's a constant in this integral. So that means that this r dr is equal to du over 2. So I can make a substitution. Now my integral looks like this. Ez equals zq over 2 pi epsilon naught r squared. And then I have this. I'm going to leave the integral as just plain. We're going to switch back to r to evaluate. I'll have another 2 over here. I'll just put a 1/2. And then I have du. And then I have u to the 3/2 on the bottom. I'm going to actually write it like this. U to the negative 3/2. And I wrote that backwards. I usually write this, then du, but it doesn't really matter. Because this is something I can do. This is just a power rule, right? I can use the power rule. So this is u to the power. I raise this by a power, add 1 to the power, and then that will be my answer. So let's integrate this. I get Ez equals, now I'm going to multiply those two together. 1 over 4 pi. I feel like there shouldn't be a 4, but I don't know. Epsilon naught z q over r squared. And then this is going to be u. If I add 1 to that, I get u to the negative 1/2, right? 2 over 2 added to that would be negative 1. I'm asking myself. And then I need to divide by the power. So I need to divide this by negative 1/2. So I get a negative 2 over here. Let's cross that out. But negative 2. So then when I take the derivative, the negative 2 and the 1/2 cancel. And then I need to evaluate that from r equals 0 to r. So to evaluate let's put back in our expression for this. So I get the 2 is going to cancel. So I get negative zq over 2 pi epsilon naught r squared, and then I get 1 over the square root of r squared plus z squared from 0 to r. Whew. I've got 2 sheets of paper left. Okay, so let's evaluate that. Ez equals this whole thing. Yeah, that's fine. So I get negative zq over 2 pi epsilon naught r squared. Then I put in r, capital R here, so I get 1 over the square root of r squared plus z squared minus 1 over z, right? Because I get put in r equals 0, and then I get the square root of z squared is z. Now let's just do a little trick. I'm going to bring the negative z in to the parentheses. So that means this is going to be plus z over z. So I get q over 2 pi epsilon naught r squared. Then I get z over z minus z over the square root of r squared plus z squared. And so that's equal to q over 2 pi epsilon naught r squared 1 minus z over the square root of r squared plus z squared. I think that's right. Let me just double check. Yeah. Okay, now let's do one more thing. No, let's check. Units. Okay, so I need epsilon naught on the bottom, got that. I need charge on the top, got that. And then I need 1 over meter squared. So notice that this has no units, it's 1. And this is meters divided by meters, so that has no units. But over here I have the meters squared. So that's a checkarooski right there, it works. Now let's check if z equals 0. It doesn't seem, it seems like it could blow up, but if you're right there on, as long as there's no ring right there in the middle, it should go to 0. So z equals 0. So if I put 0 and then this is r, that does give me 1. Oh, it's not 0. Okay, let's just put not sure. It's okay to not be sure. Z much greater than r, much greater than r. It should look like a point charge, right? So if z is much greater than r, then this is just going to be z over z. And so I get 1 minus 1. Oh, this is, well, no. I think I just need to change the form in order to see that. Let's look over here. I get, if this is going to be 1 over z minus 1 over z. Okay, again, I'm not sure. So maybe, but I'm checking my equation sheet, and I'm pretty sure this is the right answer. So I just need to think about that some more. But let's go over here, and what we normally do is, since we have this pi r squared is the area, we can actually write this as EZ equals Q over 2a epsilon naught, and then this is 1 minus z over the square root of z squared, r squared plus z squared. Now, if you're very, very close to the plate, if r squared is greater, then I can write this. So if z is much less than r, this is close, then this is just going to be r squared on the bottom. So I get EZ is approximately equal to Q over 2a epsilon naught 1 minus z over r. And if you say, you know, it's even worse, z is super, 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 super close, then this is just EZ is approximately equal to Q over 2a epsilon naught. And it's constant. Okay, so there's your constant electric field due to a single plate. Now we can do 2 plates. So if I say that one's plus and that one's minus, and then I have the electric field, we'll call that E plus, and then I have the electric field due to the minus, E minus. They're both vectors. They're both in the same direction. I add them together, and they're separated by a distance S. I think we can actually use this form to show that the electric field's constant. So let's call this Z equals 0, and this would be Z equals S. So even though the electric field does change with distance, it's still going to add up to be a constant. So I'm going to say the electric field E is going to be E plus E minus. So the electric field due to the plus one's pretty easy. It's just going to be Q over 2A epsilon naught 1 minus Z over R. Now what about this one? So if I'm right here, that's my Z value, but I need this distance right here, which is going to be S minus Z. So my distance for this one's going to be S minus Z. So I get plus Q over 2A epsilon naught. I've already included the direction. 1 minus, and this is going to be, what did I just say? S minus Z over R, right? S minus Z parentheses. So that's the distance from here. So it does decay. Now if I add these two terms together, I can factor this out. I get Q over 2A epsilon naught. And then I get this plus that is going to be 2. And then I have minus Z over R. And I'm going to make this as two terms. So I get minus S over R plus Z over R. Those cancel. So I get Q over A. I'm going to factor out the 2 epsilon naught. The 2's cancel. And then I get S minus 1 minus S over 2R. But it doesn't matter, right? S is the distance between them, and it's constant. This is constant. And if S is much smaller than R, then this would just be approximately equal to Q over A epsilon naught, which is the electric field due to a parallel plate capacitor. Boom, I did it. In under 30 minutes, I'll have to add. Okay. You can also use this same result to show that the electric field outside is very small, but not zero, which is exactly what I had before. Okay. Whew, that was a chore. It's kind of fun, though. Okay, I hope that helps.